Okay, in last class we have seen what is a Fourier series and this special case, that is 2L equal to 2 pi and c equal to minus pi. That means a periodic function f of x is defined in the interval minus pi to plus pi. Then its Fourier series is like this, and we can evaluate a naught and an and bn using these formulas. In this session we will discuss two more problems related to these type of Fourier series. Okay, consider a problem. Find the Fourier series of f of x is equal to mod x in the interval minus pi to plus pi. Hence, evaluate 1 plus 1 by 3 square plus 1 by 5 square plus etc. Okay, so first we have to find the Fourier series of this function in this interval. So we have to evaluate a naught, an and bn. Okay, we know that a naught is given by this formula 1 by 2 pi integral minus pi to plus pi f of x dx. Here f of x is mod x, so this expression becomes like this. And also we know that this mod x is even function. That means f of minus x is equal to modulus of minus x, and that is equal to again mod x, that is equal to f of x. So f of minus x equal to f of x means given function is even. So this function is even, we can rewrite this integral as like this 1 by 2 pi into 2 times 0 to pi f of x dx mod x dx. Okay, and again by the definition of mod x, now here x is varying from 0 to pi, that means x is positive, right? Since x is positive, what about mod x? Yes, mod x is x itself. Also we can cancel these two, so this becomes 1 by pi integral 0 to pi x dx, right? So this is x square by 2 0 to pi. So 1 by pi, when x equal to pi, this is pi square by 2. When x equal to 0, the term is 0. So you can cancel 1 pi, this become pi by 2, right? So a naught is pi by 2. Next we have to find an. An is given by this formula 1 by pi integral minus pi to plus pi f of x cosine x dx. And f of x is mod x. And we know that mod x is even function. Mod x is an even function and cos is also an even function. So product of two even functions, that is again an even function. Okay, so this entire function is even. So we can write this integral as 1 by pi into 2 times 0 to pi mod x into cosine x. Okay, in this interval, what about mod x? Here x is positive, so mod x is x itself. So x into cosine x dx. Okay. Now we can integrate this either using integration by parts or general rule of integration. Okay, this is the generalization of integration by parts. Integral uv dx. Suppose u and v are functions of x. Then this is the general rule of integration by parts. U into v1. Here lower suffixes stands for integration. Okay, so here v1 stands for integral v dx. Okay, and upper suffixes for derivative. So first function into integral of second minus u dash. Here u1 upper suffix stands for, so u1 stands for du by dx, right? Derivative of u with respect to x. Then what is v2? So v2 means the derivative of, sorry, integral of v1. Integral of v1 means integral v1 dx, right? So that is v2. And u, what is u2? u2 is the derivative of u1. Okay, like that. So actually u2 means du1 by dx, derivative of this quantity. Okay, similarly you can continue. So this is the general rule of integration by parts, but this rule is applicable only when u raised to k equal to 0 for some k. That means after some finite number of derivatives u should be 0. Okay, or some kth derivative of u should be 0, then only you can apply this rule. Okay, so anyway we always choose first function has this property. Okay, so I'm going to apply this rule for this function. It is clear that this u is our okay, we can choose u as x and v as cosine x. Why? U has this property. After some finite number of derivatives, this term becomes 0. For example, first function u, the second function is 1, the third one is 0. Okay, so actually in this example, k equal to 3, right? When k equal to 3, this term is 0. Anyway, after finite number of derivatives, first term becomes 0. So we can use this rule. So what is the rule? first function, that is x, into v1. v1 means integral of this v. What is the integral of cos nx? That is sin nx by n, right? So this is our v1, right? Minus u upper suffix 1. U upper suffix 1 means derivative of u, that is 1, right? Into v2. What is v2? v2 is the integral of v1. In this case, this entire quantity is v1, right? So this entire quantity is v1. So what is the integral of sin nx by n, including this n? Okay, because this is our v1. So its derivative is its integral is minus cos nx by n square, because already one n is there. So this is our v2. So this is enough, because next term is u2. u2 means derivative of 1. Derivative of 1 is 0. So all other terms are 0. So we have only two terms. Clear? And 0 to pi. The lower limit is 0, upper limit is pi. This is the algorithm. Okay, so when x equal to pi, this becomes 2 by pi. Pi into sin n pi by n. Minus into minus plus cos n pi by n square. Minus, when x equal to 0, this term becomes 0. 0 into something. So anyway it is 0. And this minus into minus plus. And this becomes cos 0 by n square. Okay. And what is sin n pi? We know that sin n pi is always 0. So this term is again 0. So this term, okay, also what is cos n pi? Cos n pi is minus 1 raised to n. So this is 0. So this expression becomes minus 1 raised to n by n square minus cos 0 is 1. So 1 by n square. So n square is common, you can take outside. So this becomes 2 by n square pi into minus 1 raised to n minus 1. So this is our an. Okay. Okay, next we have to find bn. Bn is given by this formula, 1 by pi integral minus pi to plus pi f of x sin nx dx. Here f of x is mod x. So here what happened? Here we know that mod x is even function and sin nx is an odd function, right? So what about the product of even and odd function? That is again a odd function. So this entire function is odd. The integral is of the form minus a to plus a. So what is the integral value? Yes, that is equal to 0. So all the bn's are 0. Okay. So a not equal to pi by 2, an is like this, and all the bn's are 0. Now you can write the Fourier series. Okay, we know that this is the formula of Fourier series, and we denote the Fourier series by s of x. Okay. And you just substitute a naught, an and bn. So this become, okay, so this is the Fourier series, pi by 2 plus sigma n equal to 1 to infinity 2 by n square pi into minus 1 raised to n minus 1 into cos nx, because this term is 0, all the bn's are 0. So this is the Fourier series of this function. Next we have to evaluate this infinite series, value of this infinite series. Okay, for that first we expand this one. What is our s of x? If you substitute the values of n, this become pi by 2 plus, when n equal to 1, what happened? When n equal to 1, this term become minus 1 raised to 1 minus 1. What is minus 1 raised to 1? That is minus 1. Minus 1 minus 1, that is minus 2, right? So the first term is 2 by, when n equal to 1, this become 1 square into pi, and this is minus 2, right? Minus 2, when n equal to 1, this is cos x. Clear? Plus, when n equal to 2, this is 2 by 2 square pi into the second time is minus 1 raised to 2 minus 1. That is 1 minus 1. That is equal to 0. So when n is even, this term is 0. Clear? So only odd terms are non-zeros. So the second one is 0. Then when n equal to 3, this become 2 by 3 square pi into minus 2. Again this is minus 2 into cos 3x. Next term is 0 plus etc. Okay. Then here it is clear that minus 4 by pi, minus 4 by pi, that is common. So we can take outside. So minus 4 by pi is common, take outside. And what is the remaining term? The first one is cos x, right? Cos x by 1 square. And the second term is from, second non-zero term is from this one. That is cos 3x, right? Cos 3x by 3 square. What about the next non-zero term? That is cos 5x by 5 square plus etc. Clear? So this is our expansion form of our Fourier series. So we denote this by S of x. So next we have to find the sum of this infinite series. For which value of x gives this infinite series? Okay, so yes, when x equal to 0, this cos 0 is 1. This is again cos 0, that also 1. So when x equal to 0, this is almost like 1 plus 1 by 3 square plus 1 by 5 square, etc. Okay, so x equal to 0, the left side is s of 0. And we know there is a relation between s of x and f of x. If f of x is continuous, then they are same. Otherwise, we have to take the average. Then what about this function? What is the graph of this function in the interval minus pi to plus pi? We know that mod x is like this. This is the graph of mod x. It is clear that mod x is continuous everywhere in this interval. Okay, so especially in x equal to 0. Clear. So when x equal to 0, our function is continuous. So we know that s of 0 is same as f of 0 because the function is continuous. Clear. So you can equate these two. Okay, so what is s of 0? When x equal to 0, this is pi by 2 minus 4 by pi, 1 plus 1 by 3 square plus 1 by 5 square, etc. equal to f of 0. What is f of 0? F of x is given, that is mod x. So f of 0 is 0. Okay, by simplifying this expression, you can find this infinite sum. Okay, so pi by 2 equal to 4 by pi, 1 plus 1 by 3 square plus 1 by 5 square, etc. So what is the value of this infinite series? That is equal to, you can just cross multiply this 4 by pi. So the infinite series is equal to, so this infinite series is equal to pi square by 8, right? You multiply this pi and 4, this become pi square by 8. So the value of this infinite series is pi square by 8. So this is the one mathematical application of Fourier series for evaluating such infinite series. Okay, so this is the final answer. Okay, next problem. Find the Fourier series of f of x is equal to x cos x in the interval minus pi to plus pi. Okay, so what is a naught and an? A naught is 1 by 2 pi integral minus pi to plus pi f of x dx. Here f of x is x cos x, right? And what about this function x? X is an odd function, right? What about cos x? It is an even function. So its product is odd function. So this entire function is odd function, right? So integral minus a to plus a, this integral is 0. Similarly, what about an? 1 by pi integral minus pi to plus pi f of x into cos nx. Here f of x is x cos x into cos nx dx. And similar to this case, here x is odd function, cos x is even function, cos x and cos nx is also an even function. So what about the product? So odd into even odd function. So again odd into even odd function. So this entire function is odd, right? So as similar to the previous case, integral minus a to plus a type odd function that is equal to 0. So in this example, a naught and all the an's are 0. So we have next we have to evaluate bn. Okay, bn is given by this formula 1 by pi integral minus pi to plus pi, or function f of x is x cos x into sin nx dx. As similar to the previous case, here x is odd function, cos nx is even function, and sin nx is odd function. And we know that odd into even is odd function. Now again odd into odd is again even function. Okay, so this entire function is even, right? So we can write this integral as like this, 1 by pi into 2 times integral 0 to pi x cos x sin nx dx. Okay, next we are going to expand this cos x into sin nx using this formula. Sin a cos b is equal to sin a plus b plus sin a minus b whole divided by 2. Okay, here our a is nx and b is x. Okay, so this is our b, this is our a. So this expression become, so this become 2 by pi integral 0 to pi x into sin a plus b. Here a is nx, b is x. So sin a plus b plus sin nx minus x by 2. Here this 2 is a constant, you can take outside and cancel. with these two, and here x is common, so this expression becomes sine n plus 1 times x, and this is sine n minus 1 times x. Okay, so this become, okay, so this is our expression. Next we are going to apply integration by parts, our general rule, by taking this x as u and this remaining full term is v. Okay, because this x has that property, after some derivative this term becomes 0. Okay, so first function into integral of second, that is v1. So what is the integral of sine n plus 1 x by x? That is minus cos n plus 1 x by n plus 1, and this is minus cos n minus 1 x by n plus 1, n minus 1. Okay, okay, so this is u, this entire term is v1. So next term is minus u upper suffix 1, that means derivative of x, that is 1. Okay, into v2. What is v2? V2 stands for the integral of this entire v1. Clear? So what is the integral of this entire v1? So this become minus sine n plus 1 x by n plus 1 square, because already there is a n plus 1. Similarly, integral of this entire term is minus sine n minus 1 x by n minus 1 square and 0 to pi. Okay, so actually this is our u1 derivative of u, and this is our v2, this full time is v2. Clear? And one more thing, this integration is exist only when this n minus 1 is not equal to 0, right? Because when n equal to 1, we know the bn is varying from n equal to 1 to etc. Okay, in this variation of n, when n equal to 1, this term becomes 0. We know that when denominator is 0, the term is not defined. Okay, so this integration is possible only when n not equal to 1. So we can evaluate bn using this expression only when n not equal to 1, or for n equal to 2, 3, etc. We have to evaluate b1 separately. Okay, when x equal to pi, this become pi into minus cos n plus 1 pi by n plus 1 minus cos n minus 1 pi by n minus 1. And what about this term? Here n is an integer, so n plus 1 is also an integer. So this is almost like sin n pi. Okay, only difference is this is sin n plus 1 pi. Anyway, sine of integer into pi, we know that sin n pi equal to 0. So this term equal to 0, this term is also 0, because whatever be the n is an integer, so n minus 1 is also an integer. So sine integer times pi, that is equal to 0. So when x equal to pi, these two terms are 0. Similarly, when x equal to 0, this is sine 0, this also sine 0, that also 0. So this term is completely 0. Okay, so our integral is like this. Okay, next we can cancel this pi is common. And what is cos n plus 1 pi? That is minus 1 raised to n plus 1. This is minus 1 raised to n minus 1. Okay, so and also this bn is valid only for n greater than or equal to. For n equal to 1, we have to evaluate b1 separately. So this become minus 1 raised to n plus 1 by n plus 1 minus 1 raised to n minus 1 by n minus 1. Okay, 1 minus into minus 1 raised to n plus 1, that is minus 1 raised to n plus 2, right, by n plus 1. And this is plus minus into minus 1 raised to n minus 1. One more minus is there, so that is minus 1 raised to n by n minus 1. Okay, so here minus 1 raised to n is common, you can take outside. So minus 1 raised to n into, what is the remaining? Remaining is minus 1 square by n plus 1, here plus 1 by n minus 1. Okay, and what about minus 1 square? That is 1. So this expression is like this. And if you take the LCM, so n minus 1 plus n plus 1 by n plus 1 into n minus 1, that is n square minus 1. So you can cancel these to 1. So this becomes 2n by n square minus 1. So this is our bn for n greater than or equal to. Next we have to find b1. Okay, what is b1? When n equal to 1, this become 1 by pi integral minus pi to plus pi f of x. In this, our f of x is x x cos x, right? X cos x into, instead of sin n x, this is b1, so this become sin x. Okay, so that's why b1 is equal to 1 by pi integral minus pi to plus pi f of x x cos x into sin x dx. And we know that this function is even function odd function, even function, odd function. So this product is odd, odd into odd, again even. Okay, so we can use this rule 2 times 0 to pi. Okay, and also we have one result, sin x cos x is equal to sin 2x by 2. So using that rule, this cos x sin x becomes sin 2x by 2. You can cancel these two. So next you have to integrate x into sin 2x. Okay, so this is equal to first function x into integral of second, that is minus cos 2x by 2. Derivative of first one, that is 1 into integral of this v1, that is minus sin 2x by 4. Next you have to substitute the upper limit and lower limit. So this expression v1 become, so when pi, this is pi into minus cos 2 pi by 2. When x equal to pi, this is sin 2 pi. Sin 2 pi is 0. Minus when x equal to 0, this term is 0. 0 into something is 0. And sin 0 is 0. So all the terms are 0. Okay. So what is our b1? So you can cancel now these two pi's. And what is cos 2 pi? Yes, cos 2 pi is 1. So ultimately b1 become minus 1 by 2. Okay, now we have all the coefficients b1 and bn for n greater than or equal to n not equal to 0, all the n's are 0. Now we are ready to write our Fourier series. Okay, our Fourier series is given by this formula, a naught plus sigma an cos nx plus bn sin nx. Here a not equal to 0 and n's are 0, only bn exists. So this become sigma n equal to 1 to infinity bn sin nx, and we know b1 and b2 b3 etc are different, so we have to split this as like this, b1 sin x plus sigma n equal to 2 to infinity, right, n equal to 2 to infinity bn sin nx. So what is our b1? b1 is minus 1 by 2, so minus 1 by 2 sin x plus. Okay, so our Fourier series is minus 1 by 2 sin x plus sigma n equal to 2 to infinity. What is our bn? bn is minus 1 raised to n, 2n by n square minus 1 sin nx. Okay, so this is the Fourier series of this function in this interval. Okay, and okay, this is the Fourier series. But one interesting thing is here x and cos x both are continuous everywhere. So this function is continuous. So we know that a function is continuous, then s of x is same as f of x. So we can write this is equal to x cos x, no problem. So x cos x is equal to, we can write x cos x as a series expansion in terms of sign. What a beautiful result. Okay. Okay, this is your homework. Thank you.